Hi, folks. This is 王不老 说半岛. Today, I would like to continue my talk on the semiconductor magic, chapter 15. I think you guys have uh, have seen the movie I posted, right? The Rain Man and the Split. The Rain Man is a story about brothers, Tom Cruise and Justin Hoffman. Play these brothers. This is kind of autistic, but it has a genius instinct how to count numbers, and then they have a story developed in a way that they know each other, become real brothers. Splits, on the other hand, by James McBoy, very good actor, played 24 different personality in one person. Kind of very dark and scary movie. Meaning that this split personality inside of him sometimes could hurt him. So that's my icebreaker. What I use that as my icebreaker is that I'm going to pretend that silicon is talking to germanium. They are two very famous semiconductor and they are very similar in many aspects. So my question is that pretending silicon murmuring to germanium, are you my Rain Man? It's going to help me. Or my split personality is going to hurt me, right? Especially talking about SiGe and then its oxide. And from that, I like to extend to 2 nanometer nanosheet formation because the nanosheet formation utilize SiGe as the sacrificial layer. And I would compare Intel, IBM, and TSMC from this aspect, especially about the BDI, body dielectric isolation, or punch-through stopper, PTS, selective epitaxial growth, and selective etch of silicon and SiGe. And how to achieve that in sub-angstrom control. And of course, I don't know exactly how they control in this level, but I do know that that's what they need in order to achieve a success of 2 nanometer. And as you know, TSMC announced the success, high yield, almost 90% of 2 nanometer on the first announcement. But they have something they don't even say. They did not include the backside PDN as they promised 2 years ago. Did something happen? I don't know. We'll talk about it, right? So as usual, I would throw you a lot of interesting other icebreakers that I think is important. Because I think as we say engineer, we need to extend our horizon, right? The more you understand the world, you find yourself, will be more interesting person and extend your scope in understand material and even semiconductors. Trust me, it helps. Why it's called here is we always, to try to find the other half. That is so important in our marriage. Marriage, like, we always try to find the perfect other half. Half of them, half of us never be able to find it, or we find it, we're divorced, right? The divorce rate of the US or even the world is roughly 50%. So half are failed. And the other half concept is from Plato's Symposium. He told a story, right? He said that the first generation of human being, a woman and a man, they actually share the same body. They kind of stuck together. And naturally, the other half. So they have 4 arms and 4 legs, and they are here like this. And they are extremely powerful, almost a godlike power. And Zeus said, no, that's not going to happen, right? That's not happening. I'm the god, and you are the human. You are mortals. So he cut them in half, right? He split the first human being into 2 halves. He cursed them, say, not only, I'm going to diminish your power by curse you to search your other half the rest of your life. Well, that's a curse. That's why, when we try to marry our beloved, the other half, you always had the urge, say, I want to find my soulmate. That's kidding, right? So that means that it's kind of we are born with a split personality, kind of built in, right? And then the other interesting mythology I like to share is Dionysus. Dionysus actually has a built-in split personality as well, because Zeus, as a love boys, always liked to entice girls, and then he met Hera, a beautiful young lady, and then they become lovers, and then she got pregnant, and her name is Samael, all right, and Zeus' wife Hera is of course not happy about this, right? The infidelity of Zeus pissed her off. So what's her reaction? Hera said she approached Samael and tell her, say, yeah, we were friends. We're friends now, and then we share all the secrets. And Samael, of course, so naive and confided to her that her love boy was Zeus. And Hera, of course, knew that already, right? But she said, wait a minute, I don't think so. What do you mean? Zeus told me that he is the divinity, that he is God. So no, I think he just fooled you so as that you could be with him. So go ask Zeus, ask him to prove that he is a true God. And then so Samael demanded Zeus review her divinity. Show me your God feature, right? And Zeus says, no, better not, because mortals cannot look upon gods. If you look at the gods, if he show his divinity, you'll be consumed in flame, you'll be burned to ashes. And Samael said, no, I don't think so. You're bluffing. Zeus had no choice but to reveal his divinity. And then, of course, Samael go to consuming in a flame. But at that time, she was pregnant. Zeus rescued the fetus, Dionysus, and then planted that into his side, eventually gave birth to him later. That's the first male giving birth to a baby, right? So Dionysus called the twice born is a split personality of mortal and divinity. His split personality is, pretty good, right? So mortal from his mother, and then divinity living forever from his dad. So that's what I said that the Dionysus has the building split personality. Okay. So my question for you, throughout this talk, I will ask almost every page, is germanium the main or the split to silicon? This is the metal they look like. They look at different color, okay? And they're pretty much abundant. Of course, silicon is most abundant, one of the most abundant elements on Earth. Germanium, not so, but still not too bad. It's not like, it's an endangered species or like that. No, they're not. And then germanium has some, people find out they're very interesting, okay? Actually, Japanese find out the organic form of germanium is a very good supplement to improve your health. So my comment is that, can you suggest you can eat some organic germanium, but nobody go and eat organic silicon. It does not exist. So in that sense, germanium is pretty good, right? People believe in that. You could buy it in Amazon, $20 for this bottle. You could try and see where they work and tell me, okay? And then in the modern world, I mean, they've been made into some semiconductor elements like diodes. Each one had their own specific purpose because they have a the band gap is small. So germanium has a lower forward voltage drop, 0.3 volt, you're able to drive it. Silicon, you need to drive it with 0.7 volt at least. And then it's so sensitive. Germanium is so small band gap, so it operates at lower temperature. But silicon, of course, higher band gap, higher temperature, right? And germanium is more delicate. So it has its own purpose, but prone to damage from heat, right? Of course, more expensive. And but of course, a faster response time. All because there's a smaller band gap, right? Of course, not 0.3 volts. It's 0.6, 0.66, 0.7. And silicon is 1.1. But the forward voltage for the diode is 0.7 and 0.3. So each one has their own role. So are the Rayman not split? Oh, they're not hurting each other. So they're not split. So they are not split. Independently, they are kind of a Rayman, right? They're brothers, and their own thing. So like Dustin Hoffman versus the Tom Cruise, right? Each one smart in their own way. So that's fine. I call them Rayman. All right. So let's go back to our key topic: the good, the bad, and the ugly. Germanium versus silicon. That'll be a key topic. And I will be judged. I'll be throwing a kind of a scorecard, just simple scorecard, Rayman or split, for you to decide. The first one that comes to my mind is the ugly conductivity of SiGe. If you look at thermal conductivity curve of any alloy, it should be proportional, right? This is germanium 0. It means pure silicon here. This is pure silicon, pure silicon. And then germanium actually equal to 1 is pure germanium, right? It's pure germanium. In theory, intuitively, you would think, it doesn't matter who's good and bad. It should be linear like this, right? Metal, you mix two metal together. One is a little bit better than the other. This is 150 watt meter Kelvin, and the other one is like 80, 60. So it's like 2.5x off. But it still has to behave like this, right? Linear. That's our intuition. If you mix copper and gold, copper and aluminum, that's what you expect. But that's so for this alloy. It drops like a rock. They don't behave like metal at all. They don't behave like metal. Actually, they behave like oxides. The oxide is about here, about 1, okay, about here. And here is like, 7, 8. It's not too far away from SiO2. So that's how strange it is. And the reason behind it, actually, is quite simple. Because germanium atom size is much larger than silicon. And that's why we use it as a PCG, right? We use germanium larger size to squeeze a channel to make it compressive, to boost the mobility of holes. But so that's the Rayman part of it. But here, I think it's a split, isn't it? It's hurting the thermal conductivity. The reason is that if you have a much larger atom dispersed uniformly across a matrix, a crystalline matrix of silicon, and that create a block for the thermal phonon. The phonon is one that transports the heat. Phonon is a vibration of your ions, your silicon germanium atoms, right? The vibration of that is called phonon. So germanium like move one way, and the silicon like move the other way because they have different size. Imagine you have a pendulum model in your head. So when heat waves through it, germanium will act like a thermal blocker because it's big and it vibrates different frequency. So the phonon want to travel through it, and he sees germanium blocking the road. That's the reason. A little bit germanium will drop you like a rock. 10% is dropped like so low already, right? Even a few percent will drop like a rock already. So that's a problem. Of course, I would call that a split, right? So that is damaging the property of silicon germanium, this alloy. So what is complication of that then? Well, one of the famous complication is that if you use SiGe as the stress relief buffer, SRB, if that layer is thick, microns, right? You need some microns in order to get rid of the dislocation when you grow from the silicon to SiGe as a buffer. This has been a very famous study using SiGe, right? Samsung, IBM tried to do that and eventually failed, but it has been tried for the 7 nanometer. And that is a lot of good benefit. It will stress PFA and FA at the same time. It's the beauty of it. But with that thick layer, what happened? Then the thermoconductivity behavior of the wafer will be in deep trouble. For example, if you send the wafer through this fast RTP process, very high temperature in 1 second, boom, 1000 degrees, and it comes down. Such a high thermal stress, your wafer with such a thick, close to oxide, low thermal conductivity material, you will hear cracking sound. Your wafer could potentially break if this process is too fast, too high temperature, thermal stress too large, right? So I think we agree this is a split. Right? It's hurting SiGe, all right? That's one. The other one is SiGeO2 is a piece of ugly trash. Well, next topic is rain may all split about germanium. It turns out germanium oxide is a piece of ugly trash. What do you mean by ugly trash? How do you judge that? Well, I judge it by this diagram. It's called Ellington diagram. All right, the right-hand picture is called Ellington diagram. And how do you get information about that? Let me show you how do you get that, right? That's critical. Well, this is the website I'm talking about. It's actually a website from Cambridge University. It's called DOITPOMS, right? The Promotional Material Science. They create an interactive Ellington diagram. Very nice, very nice. And so they could let you launch the interactive Ellington diagram in a new window or use this window, right? The same. So I want oxide. This is available information. I want to compare germanium and silicon, right? Oxides. See Ellington diagram. Boom, there you have it, right? This is how I obtain my information and put it here. The same thing. What that means is that, as I emphasize here, the higher you sit in Ellington diagram, the more unstable you are, right? You sit here, for example, at 500 Kelvin, right? At 500 Kelvin, this temperature, you can see that. Let's look at this. Here, about say minus 500, and here's minus maybe 800. This is the standard keep-free energy. So the lower, the more negative energy, the more stable you are. That's what pretty much it means. And here, obviously, it has a huge difference. The 250, I'm sorry, here to here is like 250 kilojoule more difference. That's significant. That's very significant, free energy, right? As a unit. This means that it's very stable. The lower you go, the more stable the oxide is. So the higher you sit in an Ellington diagram, the more unstable you are. So it's reasonable that you know this material is pretty bad, because to make a device, we want everything to be stable. When you go at high temperature, things go crazy, then it's not stable. I'm a process guy. That's what I'm worried about, right? For example, people find out GO2 vaporize at low temperature. 420 or less than 500, it will vaporize by itself. SiO2, on the other hand, are very stable. 1000, no problem, right? And GO2 dissolvable in DI water. Oh, this is horrible, because all my processes, a lot of them are DI. I need to clean the wafer, right? If I want the oxide and just cleaning it, I wash it off. What's the point? So that's give me a lot of process headache. SiO2, no, it's stable. They're only afraid of the HF, right? The other S is fine. So we can easily see that germanium in this element diagram is kind of a split, right? It's bad. And let's look at an additional split for germanium. The SiGe DIT is ugly trash as well. You look at this one. This is for SOI comparison, right? It's just for comparison. And SOI silicon, you could go to E or lower, right? You go to 5E10 DIT. That's the interfacial defect number per electron volt per centimeter squared. And this is what currency we have for the regular CMOS. That's how low it should be and can be. But if you look at SiGe, this one, SiGeOI, 35%. It's talking about silicon oxide, SiGeOI, the germanium, silicon germanium oxide, that system. Let's look at the comparison in terms of defect density. It's 2 orders of magnitude higher. This means that your mobility sucks, because defect will see that. I mean, your carrier will see the defect number. So anything above 5E10, you are in deep trouble. If you are in E11, you are probably okay, but risky. This is what the current TSMC Intel sits. Anything higher than E11, you will have a big problem, I'm telling you, okay? And if you are here, forget it. Your device will never work properly. Your mobility is so low, you will lose all your advantage, right? So all these are no, okay? And it turns out it's very strong dependence on the thickness. That's bad news too. I want a stable one. If it's bad one, okay, that's fine. But it would change to 3x when it's very thin. And I want to be thin most of the time. So that's pretty bad news as well. So overall, passivation of SiGe is a big deal. By the way, no one can passivate high germanium SiGe good enough for high volume manufacturing. No one. People publish paper, all right, left and right, about how low they could passivate SiGe, but at the end of the day, it can never really put into HVM for the high germanium SiGe. TSMC said they did it for 5 nanometer PFAB. So I think that germanium is borderline 30%. There's no way to do any higher. And I still have some doubts on that. Let's talk about that later, okay? So you can see that, so the takeaway message from this page is that SiGeOI DIT is pretty bad, right? It's obviously a split personality come out. It hurts the system. And you want to cleaning it, it's a big headache as well. So I said, okay, can we just clean it? Okay, you look at the data. SiO2 on silicon can be easily cleaned by HF, buffer oxide etch, BOE. And will leave a very smooth surface. Beautiful, atomically flat. Nice. So the So the high K that first step is high K pre-clean. That's clean the native oxide off the silicon. And it will do more clean later on, but that is the first step you do. But germanium oxide cannot be cleaned by HF. You can clean by dipping the sample in the DI water. All right. And with a little bit of oxygen, with this hydroxide, you will, you can etch quite reasonably well. But that leave a rough surface. That's nasty, right? You want to have a clean, smooth surface. So before you do a high K, that's the minimum you need to have. And that's the problem. So if you say, I'm going to deal with SiGeO2 only, maybe it could work some way out. But now you have a SiGeO2 on the surface. How do you deal with it? Silicon needs to be removed by HF. But your component SiGeO2 cannot be removed by HF. Can only be removed by DI water or something, this chemistry, which is very different from the HF chemistry. So how do you deal with this? So that's what I said here. Cleaning SiGe is a big headache. So is a remaining or a split? Yeah, it's obviously a split. Okay. So what happened if the bad SiGe pre-clean is done? So you say, okay, forget it. I can't do a perfect pre-clean. So what? So what? So what is here? For example, the SiGe source and drain. If you don't clean these edges off, the spacer here, the edges off, you will form pits. Okay. And that's going to hurt your device because you need to have a perfect crystalline structure in your SiGe. And you cannot have that with the pits. And you cannot see that. That's the problem. It's difficult to see it because you cannot do TEM on every source and drain, right? You have to do the device testing. So the import term to get a source drain back, you at least had to wait until level 1 to do some electrical test right here. You need to measure I on, I off, something like that. And this is a long process. To get you what you need back, it would take maybe a month. And imagine if something happened, you don't know, keep running and say, oh, I have a problem. And you want to come back and modify this clean, whatever. And well, there goes the problem. So yeah, you cannot cut every SiGe to check it. So it's hard. When you have this problem, it's going to hurt you a lot. So what do you do? What do you do? So fortunately, there are solutions. Applied materials say, use my Siconi. The Siconi is in situ pre-clean of SiGe. Okay. Later we'll introduce the chemistry here. This is his chemistry. His chemistry is using NF3, okay, this one, NF3 and NH3 and NF3, these two plasma. It will generate something, and then it will eat up SiO2 to form a compound, an NH42 SiF6. And this compound has very high vapor pressure, so it could be pumped away. And because of the plasma, right, well, this is the shower head of the machine. Shower head is something with a lot of holes inside, okay? A lot of straight holes, maybe some side holes, whatever. You want to make the plasma uniform. So the reactant eventually come NH4F, NH4F. This NH4F will react with SiO2, which thing you want to remove, and you will form a compound that can be pumped away. That's the idea. And why use the chemistry? Because it could react with it would react to form these chemical reactions at 180 degrees Celsius. You don't need pre-bake like People use like 850 for hydrogen. So I want to clean my wafer. I will use 850 degrees Celsius hydrogen. That will clean the wafer. You will vaporize. You will reduce this SiO2 into Si, etch, and vaporize away. But you cannot do that for many steps. The temperature is too high. So you want a low temperature solution. The reaction temperature from Siconi, the advertisement. People use that. They're giving that. So this is the chemical process. It worked. You change into a solid and then you will vaporize. It's sublime. This solid can vaporize easily. And that's the beauty of it. Okay. But is that enough? No, that's not enough. You look at the actual process. The actual process, this IMEC work, I think did a pretty good job. It do a lot of experiments. I try to find a solution to improve, to get rid of oxygen as much as you can. So what's the POR process? Well, POR process is here, HF and HCl. These two tanks, you went through the machine, the wet bench. You take the wafer out and you run. A machine will run, a conveyor belt will run, and put it into high K machine. But at the moment you take out from the wet bench, you start to oxidize. The oxides come back in 30 seconds. So you have to do in situ. And so if I do in situ, meaning that it's inside the chamber of the high K, can I avoid HF as this process? No, you cannot. If you do Siconi by itself, it's still high. You have to use a combination of everything. So he went through three wet benches, HF, SCL, SC1, 3 wet benches, and then Siconi. And you may have to add in the make it even better. You want to reduce the queue time. You need to run 15 minutes. And so, wait a minute, I can't control that, right? It's the machine's running and there's something else happening. Well, that's a cost. That means that is a limit for this solution. So how good eventually they can do? The minimum reported around this paper is 1E20. If you calculate 1E20 to find out what is the surface contamination, it's about 1 or 2% or 3% of oxygen remain. So it's not perfect, but that's the best it can do. The current technology can do. All right. Well, who's his competitor? The SM Previum. Previum said I can do a better job. Why? Because they claim they can remove SiGeO2 here. Siconi did not claim that. Siconi tried to do that, but it has difficulty. And why SM can do that? Because he said, I add additional hydrogen plasma, hydrogen radical, into this remote plasma unit. So they introduce additional radical. The hydrogen here do some magic. So they said, wow, I reduce my SiGeO2. Okay? So that's what they say. But, every company will publish their machine advertisement. But at the end of the day, which one is better? Or you need to ask TSMC or Samsung or Intel. What do they do? Here, this is 2 reports I can share with you. Each one has their strengths and weakness. Okay, the HBM, when you run mini wafer, that's the final test. This is their secret. Their secret sauce. There's secret sauce everywhere in your semiconductors, and the process is very similar. But each process have to be optimized, and that optimization, not even the equipment supplier will know. Only the HBM guy who run in the fab knows. They will not tell them to the supplier because they're afraid they're going to share with their competitor. That plant material, Siconi, everybody's using it, right? Samsung's using it, TSMC is using it. Intel is using it. But why Intel, I mean, Samsung, oh, I'm sorry, TSMC wafer is the cleanest? Tell me, right? So obviously in this aspect, yeah, it's I would say, SiGe kind of empower each other. And they are difficult to deal with. Here is the when you oxidize SiGe, what happens? I call it politically incorrect, meaning that it has some prejudice against one to the other. When you oxidize, say you have a SiGe alloy, 80% silicon, 20% germanium, that's typical. Right? People use right now like close to 30%. 20% is fine. And you oxidize it. What do you see? You see they will form SiO2 preferentially. And then you will form a germanium-rich layer here. Because germanium cannot go anywhere. Silicon go and get some oxygen and oxidize and become SiO2, and germanium is left behind. On top of that, germanium oxide will not dissolve in SiO2 matrix. Silicon oxide, once it forms, it kicks the germanium oxide out. The solubility is less than 0.1%. So with this two, you get a problem. This means that when SiGe oxidizes, and SiO2 will form with small inclusion of SiO2, GeO2. So this means is SiGeOX is formed on the interface in pretty much the whole layer. So what do we do with that? Well, it's okay. They could do something. They use this one and say, actually that's good. Let me show you why. Because they will form a compressed CTOI, right? And that is what they use for the 22 FDX. This is a beauty. IBM don't care. They invented eSiGeOI, and is it HBM? Yes, they are. Okay. And that's IBM ingenuity at work again. They're smart. Very innovative company. And this is called condensation. What it means that if we put a SiGe 0.1% on top of SOI, right? This is 10% SiGe OI, or not SiGe OI, just SiGe, 10% germanium only on top of SOI. It's a top silicon. And condensation, meaning that you just heat up to very high temperature for, say, 1050 and 900 for hours. And you oxidize the top layer. We mentioned that it will push germanium down. When you oxidize it, it will form SiO2 and you'll put the germanium down, and germanium will interact with the silicon here. It will be combined with them. So if you use a very thick layer of germanium, then you could have this new silicon layer become SiGe germanium with a higher germanium content point, whatever percentage you could put it in, right? Very high germanium content. Of course, you don't want to use it too high. Anything above 0.3 uses. This one just for demo, Usually we go about 30%. So you could manipulate the layer here, the content here, and then you could design any germanium content layer that you want. He's a French guy, Vincent. I know him very well. When I work in IBM in Albany side, they developed this long time ago. He's a French guy, innovative guy. Okay, and that's what happens. They put a CT here and then put an extra thin, extremely thin SOI silicon, and then eventually they merge, got silicon germanium. Then you say, wait a minute, what about SiO2? Well, so they clean it off, right? They just wash it off by nature. And they show that, wow, it's beautiful. So this work is done, the actual device. So this is the actual 22 nanometer, okay? And this the actual device, very beautiful, very nice work. And this is what they finally achieved. Okay, so 22 FDX is 28 nanometer bulk high-k metal gate. So high-k metal gate process technology, I think it's gate first. Okay, that time, and they have a hybrid SOI and a hybrid bulk, and they have this SiGe channel for P, silicon channel for N, and then they do their device, source and drain, contact, whatever. So 22 FDX, currently GlobalFoundries still using it. They are number one in the world in terms of this technology. So if I want to grade this guy, it's called Rainman or split. Obviously, it's a Rainman. SiGe helping GlobalFoundries to dominant in FDX, FDSOI technology. They are dominant. They have many new inventions come out from here. I mean, many process optimization. Here is another example. They published in IBM 12. I think I was there. The Chen Guo, good guy, is a very good guy that he has so many patents. He has 2,000 patents under his belt. It's probably number one patent in IBM. It's master. You see here that they find out that if you do the SDI first, that's what people do, right? For our device, we put SDI, channel is here, and that's it. The reason they say it's not working for SiGe condensation is that when you deposit SiGe, you always have the facet here. A facet here, when you condense it, when you merge these two, they will have still have a facet. A facet here, you have a SiGe etch thinning. This is a no-no. The channel thinning meaning that you have a problem with reliability seriously. Right. So they say SDI last. So this is what they propose. Okay. They still put SDI, still kind of SDI first, but the SiGe here, they protect the SiGe here. Eventually they polish away. Right. SDI late. Okay. So this SDI last eventually make a flat surface. And that's the call SDI last. That's because they put it here later, right? And this is SDI first is on a pattern wafer. SDI last on a blanket wafer. That's the major difference. And it worked beautifully. This one has been with them forever. It's still running right now. If you buy GlobalFoundries wafer, they improve this process technology to about 20 nanometer. They try to do 18, no. Samsung said they are working on 18 and probably okay. I did not go investigate. But there's no 15 and 12 FDSOI. They cannot scale. I mentioned that in my last talk. Why FDSOI is so difficult to scale below 20 nanometer. Extremely hard. Too many Achilles heel. But you say, wait a minute. TSMC has it, right? Has it fine. Look at TSMC. They said this one, high mobility channel, is so tall at 40 nanometer, and then 6 nanometer width. Vertical. So perfect, so perfect. How they did it? They claim that they're 5 nanometer PFAT. Not planar, right? This is FinFET. And they don't need SOI wafer. They don't need the condensation we just described here. There's no process like that. And they put it vertical. How can you put do this process using this one? It will never work. Okay. And they did it by local condensation with this pattern. So they have a foam fin and put something around it, and they heat it up, condense it. So the fin, silicon film, turned to a SiGe fin. That's a condensation, but it's a local one. So if I ask you, germanium in this aspect, is a Raman or a split? Obviously, it's a Raman, right? They're helping silicon germanium to get into SiGe with a higher mobility. So this is what they reported out. My question to TSMC is that there's no report about 3 nanometer. Are they using SiGe or not? I did not find it on their website. If they did, they will announce it, right? Why did they not announce it? It's a big deal because they are the only one in the world that could do this. Intel cannot do that. And of course, Intel doesn't even have 5. Samsung have 5. They did not do that. They cannot achieve this. This is the only one in the world at TSMC, but they did not make a big fuss about it. I don't know. That I don't know, right? So maybe they announce it, but maybe in some product, not in every product. So I am a little bit suspicious. Yeah, that's just me. I consider myself a engineer that question everything. Okay, that's what we should be. Okay. So I'm talking about sacrificial SiGe for nanosheet formation now. Is a Raman or split? It looks like it's a Raman, right? You are helping nanosheet formation. Of course you're Raman. You're sacrificial. So what are the complications then? That's a question I want to ask. In this section, I like to explore SiGe role in the silicon nanosheet formation. Of course, my question is the Raman or split as usual. Let's look at what they say. Now, there are 3 top guys doing that, right? Intel, Samsung, TSMC. And the ribbon. This is they say we'll do first half of 2024, and right now we have third quarter, fourth quarter of 2024. They have not do anything yet, right? This company is feel so bad for them. And look at their nanosheet. They call it nano ribbon. 4 stack, 4 silicon channel. This is very nice epi work. I'm telling you, they're so rectangular, so nice. This is much better than IBM work. And they said did that they had 20 angstrom, 2 nanometer. So Intel's always do this. They do a little bit name tweaking. 2 nanometer, they said 20 angstrom. What's the difference? And then people call nanosheet, they say, I don't want to call nanosheet, I call it a ribbon. You know, just like FinFET, they don't call it FinFET, they call it Trigate. That's so funny. Yeah, they always do that, right? And so the number of nanosheet comparison, Intel, TSMC, and IBM. IBM is just like Samsung. Okay? They transfer the technology to Samsung. So IBM is helping Samsung to develop this. They are pretty nice. Ribbon, TSMC, IBM, when they publish, they were reasonably good. Nobody had outpaced each other one. The one that's distinct, stands out is the number of sheets. Intel had 4 sheets. More currents, because the more sheet you have, the higher the current you have, right? It's just count the numbers. But the others have only 3. And IBM advocate this one, this layer. It's called BDI, bottom dielectric isolation. The others didn't have it. Say here, no. TSMC, no, right? Only IBM, They like this one. It's like their SOI, right? They are the only one in the world using SOI in terms of advanced CMOS. So there's a big difference in number of sheets. And some people say, well, you look at the nanoribbon, right? It's just a thin flat. They print to line flat. It's gone flat. Just flip this thin flat and make this instead of vertical, make it horizontal. And is that true? Well, partial truth. You look at it that way. But FinFET gate control for the short channel effect has three sides. This side, 1, 2, 3. Three sides. But the nanoribbon or nanosheet have four sides that control all sides. The gate control everything. All sides of the nanosheet. And compare with the three sides here. Right, it's three sides. Four sides, of course, control better. Therefore, they have the better performance with the same voltage. That's the beauty of it. But okay, you flip it and then you have better control. So everything is good then. Not true. You lost 110 hole mobility benefits, big time. You look at the FinFET. FinFET channel orientation is 110. And then the nanosheet is 100. This surface is 100, not 110. And here, this surface here, the vertical surface here is 110. 110 is very good hole because it's higher atomic density. Hole is the way electron move without electron. There's a hole inside, right? And you want to be compact. Right? 110, higher atomic density, hole like it, so hole move faster. So FinFET is very happy. They got a hole mobility booster, but built in. This one is why FinFET is so successful. By nanosheet, you lost it. Make flat. So wait a minute, I have a vertical here. That 110, can I do that? Yes, you can, but it's nowhere compared with this one, right? So you look at the data. Their hole mobility, they drop 3x. 238 to say 80, 240 to 80. So this 3x, more than, close to 3x reduction in terms of hole mobility. Electron mobility getting better because you are lying flat. And 110 is not that good for electrons because the DIT is higher. And here, you need to mitigate it. You need to compensate that. You lost big time in your mobility. You need to figure a way out to do something. Now look at let's look at the planar MOSFET, right? They use SiGe to squeeze. This is a 45 nanometer famous Intel picture, Scott Thompson, right? That they have this strain because this guy is big. This guy is big boy. He squeezed the channel. So here's compressive. And that squeezing, on top of that, you have thermal gate removal. And that you get your highest compressive strain. Stress here is about 1 giga to 2 gigapascal. By the way, you need to have a thermal gate removal, right? Which means initially when you do a source and drain growth, eSiGe, source and drain growth, you don't get this strain. You had to remove this the polysilicon out and put your high K in. When you remove it, the things relax here. When you relax, that's where this happens. When this channel is when you take the atomic gate out, this becomes zero, becomes free space. That's the time the channel can really be compressed. So they will move in a little bit more that really capture the stressor effect. And then you put it back on, your high K metal get back on, then you maintain the strain state. There are two processes, okay? To get a complete Raman effect, the germanium in this case is obviously a Raman. You compress the channel by doing SiGe. This is you remove the silicon out and put a SiGe in, and then do this diamond gate removal. These two processes to make it work. Otherwise, it won't work. All right. If you don't have this process, it won't work. You get a little bit improvement. That's it. That's not enough. So Nanosheet used 110 surface, right? It lost the 110. It used 100 regularly. And so some people suggest, why don't you use 110 flat surface, flat wafer to begin? I actually recommend that a long time ago. And it turns out I cannot do that. Because the silicon wafer, when you grow it, you have problem. You cannot grow 110 easily. You had to use 110C to begin with, all right? You cannot just cut it. Say, I want to get 100 and cut it like 45 degree, whatever, and get 110. It won't work that way. You will not get a perfect 110. You have a little bit off, you'll be in trouble. So that's not good. That's not good. You need to have a 110, pure 110 single crystal. And you have to grow from silicon 110C. The C, you planted the seeds to grow your crystal, and that has to be 110. So in general, overall, it's just expensive. And on top of that, it's very difficult to grow 110 epi because the growth rate are very different. So the idea been dropped. Many people try, Intel try, everybody try, IMEC try, they all failed. Okay, so not that easy. So, but if you can do starting wafer, what about this? IBM in 2020, 2021, they proposed this. How about this do in situ? I call SiGe cladding growth. So I have a silicon here, and you trim it down, trim it a little bit off. Okay, oh my God. So this is about 5 nanometer, and you trim it like 2, 3 nanometer. Okay, so you see here, 3.5. And then you put cladding there, and then you heat it up, do the condensation as if you are trying to do this. You are trying to do this. For the ETSOI, you put SiGe here, and you condense it. So I want to do the same thing for nanosheet. Can I do that? Can I do that? The similar idea, like condensation, and go, so force germanium to diffuse in. Can I do that? Not by condensation, just annealing, just pure annealing, right? There's no oxidation here, just pure annealing. Can you do that? Yes, you can try that. And this is simulation results, not real data. Can it be HVM? That's a question. Can it keep uniform? All right, that's a problem. If you cannot get in uniform, then you're doomed. Okay. And I'll talk about this. Intel, IBM, TSMC mindset about this. Let's look at what's the problem with this approach. It turns out, IBM find out that germanium concentration for a very, very tall SiGe, this is a SiGe thin. If you're going through some kind of a high temperature anneal, if there's oxygen inside, what happens? What happens is that you look at this, the edge here become higher germanium content versus center. Center is what you already have, right? You say you have 30%. Okay, you have 30%, you grow it. But when you later in the process get some high temperature anneal, there are tons of them, by the way, right? The IOD 0, that's a steam anneal, oxidation. That's oxidation right there, steam anneal. Okay, or SDI anneal. SDI has a steam anneal as well, right? then you will see that the edge has a higher germanium content. So this means that if you have higher germanium content here, you're doomed. You lost the control because DIT is very different. You lose your VD control definitely. So there you go. It's a beautiful idea, right? And then you'll be in deep trouble. On top of that, let's look at this another concern. When you do here, when you want to do cladding on top of here, you need to remove the native oxide out of silicon, right? Use Siconi and something like that. And if you do a too higher temperature, what happens? People use this is what happened if you use high temperature anneal. It will reflow to become a big ball. It will deform the shape because germanium reflow easily. And you need that germanium, you need kind of remove the native oxide, but that pre-bake is hydrogen pre-bake. Hydrogen pre-bake will make this germanium or silicon germanium like a ball. The reason is that it will increase the mobility of the atomic surface diffusion of the material, of the hydrogen do. Okay. So you have to use Siconi and SM Premium, but it's not an easy task. That's my conclusion. And on top of that, you still had what do? You keep telling me you want to do this, right? And then you lost the 0.10 surface benefit from FinFET. You still had to go back to here, right? You had to go back to this structure. You still have to go back to this kind of structure. Ignore this one now. I'm just using this as an example. You need to have the eSiGe here, right? And this is a fancy one IBM used, but it never worked in SBM. This one never put into practice because of this layer. This is a great idea. It could provide tensile for the silicon, and then this compressor for SiGe, P, and then N tensile. And this is what you want. So beautiful, simulation-wise, perfect, but never in SBM. So my argument is this. TSMC 2nm success, it happened in such a timely manner. It did not introduce a new eSiGe process. This means one thing. The POR process worked wonders. And small tweaks. I will talk about the 2nm in detail later. I have a section called 2nm deep dive. We'll talk about that later. But there's no revolution changes required. It doesn't even include gallium doping for contact. This is critical, right? Because the contact at the contact that point, you need very high doping. Gallium seems to help borrow. People try that a lot, but I didn't see that, right? So that POR is so nice. Okay, they just use this process. It's good enough. Not exactly the same process because there's no E-in. Film does not have it. Film don't have this diamond edge. They cannot have it. Okay. And so overall, TSMC seems to use only POR process. Right, that's what I'm arguing. This is called eSiGe ISBD, in situ boron dope process. It's the way to go, similar to this. Okay. And now I'm going to move on to another topic. It's called the infamous but problem. The S problem, the but problem nanosheet FET. Right. And this is one I want to, every company approach differently. Let me explain what happens. There's a special but problem. It not only happens in nanosheet, but also in FinFET. Like this fin. there's a conduction path beneath this fin, right? This is called, I call it butt problem. And this problem is more severe in a nanosheet because here it's wider, right? The fin has a very small area here. So the butt problem, the conduction path is kind of a much less than if you have a wide, not a fin, a wide nanosheet under it. But this problem for nanosheet is easy to solve. It's solved by an implant called punch-through stopper. Punch-through stop means that they put a high doping here, create a local PN junction to block the pass, right? That is, for instance, this end fed, they put a P doping here, then kind of stop it by the energy barrier from the PN junction here, right? But for FinFET, what do you do with, how do you block it then? How do you block it? It turns out everybody has different ideas. This butt problem looks here. Okay, this butt problem, actually, I want to show you that this graph is better. This butt problem, I think Intel did a very smart experiment to review the big problem under nanosheet. And I think that this is a wonderful experiment they did. What they did is that, okay, you have some silicon germanium under it, and then you have, this is a normal planar PMOS. You have a 30% PMOS, so the leakage is kind of going through here. This is your leakage path. Using a planar structure to simulate the nanosheet. And nanosheet, on the other hand, there's here, okay, pretending you have a one stack. This is bottom, right? You have one layer of nanosheet, just one layer. Just demo the problem here. And you look at the leakage here. The planar, this is your butt for one nanosheet. The planar structure, you have a leakage here. And then for the gate problem, all right, you have, well, I don't want to call it bad. I call it bad here. Bad. Is it really bad? I'm not sure. I'm not sure. I don't want to say it's bad. If you look at the results, the actual results here, this two curve is for this, right? One for 0.050, one for 0.50. And let's look at the V0, the VGS gate 0 here. The leakage for the planar structure, this one, is 10 to the minus 12. But if you compare this one, the gate control is kind of weak. Here is kind of strong gate. This is a weak gate control. The leakage, wow, 10 to the minus 12 to 10 to the minus 4. That's 8 order magnitude higher. So bad. It's bad. Weak control. Okay. Because something's, imagine, if you look at this gate structure, it's interesting, right? The whole gate is controlling this. It's kind of strong control. And here you put a nanosheet here, kind of shielding the gate back with some gate control here, some control here. Not good enough, right? So this is the message, right? It is a serious problem. It is a problem. So what are you going to do about this? That's the key. And it turns out, classically, we treated instance that just pumps through stop. And how to get a dopamine inside, remember Intel has this solid state diffusion. And you cannot do that in here, right? You cannot do that in nanosheet here. It's too, the sheet is too wide to do that. So you cannot do that here. Can you do PTS then? That's the question. POR is PTS. You're using a high doping punch through stopper. It's POR for this type of sub fin leakage. And the complication is that we're going to do it. Power energy stack formation or after, which means thin reveal like FinFET or not. So that's concern, or using some complete different approach. And it turns out Intel and TSMC stuck with PTS. They don't use, I don't think using the fancy one like IBM. IBM say, well, I want a fancy. I want to block the leakage from the get-go. I will place my dielectric material under the source drain. So there's no way to do any conduction, right? Because there's no source and drain here. And see how many, and so that's what they plan first generation to do. So this, I want to do that. So it's bottom dielectric insulation under source and drain. It's better than, this is called better than, more preference, better than PTS. It's not greater than. This symbol means, qualitatively better. And it looks like it's good, yeah. It on the simulation, it's always good. And they did some work here, and it's doable, right? But it's HBM compatible. That's the question. That's the question. They did some demo and show some die is good, and they do improve a little bit here. Is that really good enough, right? This curve here, is that enough to try to change this dielectric insertion? Question. But anyway, IBM is IBM. They always innovate. Right? Doesn't matter the cost or the, whether they're going to be perfect. Don't care. And they come up with better one. 4 BDI. That's just good. Let's just put a SOI under it. This is SOI. BDI layer complete. But it actually, it doesn't matter how you create it. You could do SOI, or you could etch it off and put something inside, right? That's what you can do. And they did it. Good results, interesting. It's a costly solution with additional issues. I'm afraid that there are other complications. What kind of complication you have? Because source drain epi is not easy. If you look at the source drain epi here, the source drain epi, if you grow source drain from a typical nanosheet, here, remember, here is Siconi channel, and then there's spacer here. So it's difficult to grow a perfect one, meaning that the grain boundary will merge here and create a kind of a defect here, something here in a way. This is all defect. Horizontal, vertical defect, it will relax your strain. Okay. eSiGe, this because they have multiple surface, right? So surface here, okay, and you don't want to hear the spacer, you don't want to be here, and you want to be here. But how do you know it's perfectly the same grain boundary, the same grain crystal orientation? You don't know, right? It's a mixture of everything. And here it's not perfectly flat, right? It's like this. And even at the same crystal orientation, you still have the same problem, because when you grow from here, the growths are different. And eventually will merge. When they merge, you will have defects, right? Nothing can merge like liquid. This is solid. When you merge it, you will have air gap, 1 nanometer. Poof, you're dead. Because 1 nanometer, here is like, say, 10, depending on which dimension, 10, 30 nanometer. And 1 nanometer, that's 3%. 3%, your strain is only 1%. So you're doomed. Okay. So in theory, eSiGe stressor should either be gone or see huge variation by simulation. But does this really happen then? Is that true? I kind of doubt it. Very strange. I'll explain to you later. eSiGe designed to have 1 to 2% strain. This means that threading dislocation density or stacking fall, the Berger size vector is 0.5 nanometer. So anything with the grain boundary with the dislocation, in theory, you could diminishing the strain to 0. That's true, but is it really what happened? We'll talk about it later. Okay. So POR, I'm just here, I want to share with you, the POR SiGe is challenging already. This is a typical planar structure, right? This is what you want. You want to have perfect like this. But when you grow, you saw like facet everywhere. The process called the in situ doped, boron doped, in situ boron doped epitaxy. It's kind of selective epitaxy. And when you want to do it, you have to, first of all, remove some layer. You need to remove a plasma damage and naked oxide removal. So the first layer here, you have to do some work to remove it, to clean the surface. Okay, you have defect-free epi layer. Your C layer had to be defect-free. So you have nice, you have a nice source string. And you want to grow in this way flat. You don't want to grow it like this. That one you don't want it. And you don't want to and you need to optimize boron doping. So the doping here, the first layer should be very low doping, right? Why you need a very doping and low doping here? Because if you high doping here, then you will, when you heat up, the dopant will come into a channel. So you lost your channel control. Your LG is no longer what you defined. And that's this part is called the extension, right? EXT, the source string extension, SDE. Source string extension is very hard to engineering. This is just schematics. And then the growth rate for each surface are different. You look at the growth rate, right? In the 110 and 111, they are, no matter how you tweak it, they are different. That's the message. Here, this guy tweaking away, so it's close. But 111 to 100 is very poor. So no matter how to no matter how to tweak it, right? And so this is where the hidden jewel of a foundry, how they perfected their source and drain growth. That's how I call it a solid baseline. If you don't do this this process well, you're screwed. Let's look at the IBM. It looked nice though. They did a growth from here, right? And they have to grow it thicker. This is called the raised source drain. They raise it, right? They raise it. But remember, this is only very thin. They are only less than, say, about 6-7 nanometer. So you start on a very thin layer and you want to do epi. SOI, some pictures say nice, but it's just some pictures say nice. Not everyone like this. Keep that in mind. They publish because the result is good. They pick a perfect TM picture to show you. Right? But here they have a problem here, right? So this is a problem. So this is for their 22 nanometer. Worked. But when you want to scale, say 12, even lower, you have a problem. We talked about that last time for FDSOI, right? These are a bit thinner. Then you have a problem. And you want to grow thinner epi with a thinner SiGe layer. That's a big problem. Why is that a big problem? Because, okay, when any epi, when you grow from a lot of area, a lot of silicon, it's much better if you grow from no or thin silicon, silicon. The reason is this. If you grow epi, say 1 nanometer, will that work? It will never work. Because 1 nanometer is highly strained. Remember, this is box. And then you have a different material on top. Box as oxide has a very different crystal structure, right? the density is lower, and silicon is very dense. So naturally, the silicon on top will, no matter how you form it, when you thin it down, you'll be highly strained by nature. And when you grow an epi from a strained, thin, super thin substrate, you have problems. That's how nature works. I'm sorry. That's how it does. So 6, 7 nanometer, okay, but anything less than that, probably not. And these guys propose another way to solve the problem. Say, may not be as punch through is hard. Let's do PIN. PIN is stronger than the punch through with the same say P++ here, right? You could do it P++ here. He said PIN but different directions would be great. All right, that's the idea. That's the idea. All right, so this is kind of, I think that's more interesting. This one you could do a doping implementation, so you are at cost by additional mask. That's all. Good? No, not good. Anything adding one mask is not good. It's this is a paper just published this year. So my question is, has TSMC use that? I don't think so. Okay, I don't think so, because there's no patent published from TSMC showing that. So at the end of the day, I want to compare IBM, Intel, and TSMC in terms of mindset. The mindset they have, the engineer they have, when they see a problem, IBM say, I need a new solution. And they will flip the chain, they flip the coin and change it. But they have a limited concern for HBM. TSMC, on the other hand, a POR, solid baseline is everything. No change until last troubleshoot is exhausted. Okay? In this aspect, is risk averse. So see, they never publish any innovation. I mean, brand new process innovation by themselves. You look at every structure they come up with. I just say, I have a better job. You invented that, like cobalt, like the COAG, everything ever until IBM invented it. But eventually the yield sucks. I, on the other hand, have a perfect yield. So when I do a change, I will evaluate it. I will see whether I need a change. And PTS, they could be good. It could be good enough for them. So the reason I know that, I sense that, because they never publish anything other than the POR. Their new 2 nanometer invention is purely just some other incremental changes, not revolution. They did not say, I'm a brand new BDI, I'm going to beat everybody. No, I didn't say that. Intel is somewhere in between. They failed miserably at 10 by many innovations, the air gap, cobalt, as contact, blah, blah, blah. BDI, I didn't say BDI, backside, BDN, right? And then the first, they did have a solid 14 nanometer, but when they moved to 10, they failed miserably. Okay. And they move slowly. They fail and they want to go there very slowly. Meaning that the new changes they create, they have a hard time digesting it. TSMC, on the other hand, when they digest it, they digest it very nicely. They make the process healthier and stronger. And we'll just discuss that more. Okay. So let's continue. Germane nanochip formation, the SiGe stack. Let's come back to SiGe epi stack. So my question for you is that in germanium SiGe, germanium is a split or Raman. It acts as a Raman for sure, but sometimes I think it's duality here. It's also a necessary evil split nanosheet. The reason is this. We're doing nanosheet at 30% here, happening here. But how thick we could put it in? If you do this, right? If you do this, the theoretical most stable is like 8 nanometer. That's it. We'll show the calculation to you later. No, let me show you right now. Here, this line, somebody calculated 1.7793x power this. It's an empirical formula. This one, 8 nanometer is 0.3. But your nanosheet stack is what? 3 or 4 nanosheet with silicon is total 50 to 80 nanometer total thickness for the nanosheet stack. So you are in this region, but it's not this, it's very little defect. In theory, it could be very defective. In theory, it depends on how you grow it. And this metastable region this is the region talking about, or region talking about. Okay? And this region are temperature dependent, how you grow it. And metastable means that it's not bad, but it's not good either. If you go over to the dark area, you are relaxed with dislocation. In here, you kind of hang there. That's why it's called metastable, meaning that it's not stable, but it's not relaxed yet. It's somewhere in between. All right. And if you don't treat light, it easily can be defective. So the question is metastable always stable? It depends on temperature, of course, right? So it's not. It's not. And on top of that, if you look at the IBM, if they want to do this one, this layer actually, or this one. I think that's what I meant. This is the picture I want to show you. IBM with the body like dielectric one. And that one will clearly show you what I'm talking about, the BDI, but from the here, this one. Do you know how they did this? This is another SiGe layer. And then later, they take it out and put the electric in. But initially, it was there. This one is SiGe with higher germanium content. This one is 30%. These three 30%. The bottom one, that one, SiGe is like 50%, something higher. And so, okay, so you need to host the thickness here. Complete thickness is that's 80. That's 80. That's 80 nanometers. And then you have some high germanium content here. So, I want to put 50%. Look at the 50% here. The metastable is less, very sensitive. And then the stable region only 4 nanometers. So your epi metastability is pretty bad. Pretty bad. Okay. And this is one thing I want to stress. On top of that, germanium problem. Germanium has much lower melting temperature. So if you have a problem when you grow the stack, it will diffuse to silicon. On top of that, okay, we talk about poor thermal conductivity. That's fine. I mean, you eventually can take it out. So that's probably okay. But here, that's a big problem. And we always said that you cannot be too thin. This layer at TSMC, Intel is about 5. Anything less than 5, you're in trouble. Look at this bottom curve. This is a quantum mechanical effect. If we go below 4, then your surface potential is a strong quantum effect. That means that you cannot control VT. You're doomed. Right? So you cannot have anything. Fin is the same. Fin value cannot be less than 4. Less than 4 meaning you have 3, right? Because of process variation. So that means that you're doomed. So And how do you control it? Look at the control. Silicon thickness less than 4 nanometer, you will lose VD control. And one monolayer is 1.36 angstrom. So 5 nanometer here is 37 layer. But T silicon mask greater than 4, so your process window only six layer. And 6 layer means that when you do high HVM, your SPC control has to be sub-angstrom. That's what I meant. You cannot have 1 nanometer variation. That will kill you. So this is a complication. And that 1 nanometer could hurt you because of what? The thermal diffusion. Germanium loves silicon more than silicon loving germanium. Germanium like to go into silicon, but not the other way around. It's 2x. The diffusion coefficient change is like 2x. Look at this curve. The blue line is always more than 2x of the silicon line with different germanium concentration. The higher germanium concentration, the worse. 25% is 2x. I mean, if you're 30%, it's much higher. So this is like that. What does that mean? That means that once you form, initially you may be a perfect, not diffusion, but later on you will see it. Because many high temperature anneal, before you remove the SiGe, remove the sacrificial layer, for example, HDI anneal, you cannot use high temperature. IBM showed that. IBM said, what, this silicon, SiGe, see, germanium coming in, right? Coming in. Higher percentage. Because SDI temperature, 900. Actually, SDI temperature 900 is kind of low. It depends on process. Some people use 1000, spike anneal, super high temperature. Because you need to form a beautiful oxide. That's what SDI means. Shallow trench isolation. That liner, so it's just not the SDI. This SDI anneal meaning is anneal for liner and anneal for the bulk. Because you cannot put perfect oxide there. You have to use some kind of CVD process. And you do some kind of liner to oxidize the trench. And then you stuff it with some easy oxide because it gets you high aspect ratio. And you anneal the high temperature. So there are multiple anneal, many anneal. High temperature process and SDI. Once you finish that, you'll find some diffusion of germanium going in. Because we have how many layers? We need to control 6 monolayer. I mean that it's not just at the moment you're manufacturing it, but also afterwards. That's the tricky part. Okay. That's the tricky part. And on top of that, there's another problem. I call familiarity breeds contempt. Stiction. So when you these things are so thin and so thin and so small. After some wet clean process, whoops, because you have statics, they're stuck together. What's the difference? What's the distance between here? It's only 10 to 15 nanometer. You cannot go over 15. Go over 15 is useless. 10, below 10, there's no process. So like between 10 to 15. So such a small separation. And these are all highly strained initially. So it will be easy to stuck together. Okay. There are serious stictions. There's a residual stress everywhere after SiGe removal. And how do you relax stress? If you don't remove it properly, or you still have it, by the way, but you have some static. And the static from the wet clean is very famous. So you need to do something. And so they say they have a process. Optimize IL to remove the stiction. I think it means that he's doing some some oxidation or something to make sure the surface are, no longer metallic, beautiful thin layer oxide. I think that solves it kind of strengthens the material, right? Or remove the statics, whatever. And the issue later on developed is selective etch by in situ HCl. So you wanna do sacrificial etch. So you want to etch this one off, right? This had to be removed. This is what I call the selective etch. Okay, selective etch, and classically use in situ HCl. And it is doing in the early study, it's fine. It's pretty high selectivity. And then you just need to add a small chamber or in situ process HCl vapor inside your SiGe chamber. That's fine, etch chamber. It's okay. But it turns out, no, it's not. I see Michael, I think this paper is very nice. It's showing you that, see, SCL etch rate is strong dependence on the thickness. The slope is 18. Oh my God. Right, so this is horrible. And then here, look at the etch time. So seeing layer here, such a high roughness. So this process no good. The roughness is like 6. See, this Angstrom already. 5 Angstrom, no. You need a sub-Angstrom control. Okay. And so this is no good. So everybody's doing that, and that's what I meant here. A very finesse selective etch is required. You have a stitching here, stick together. If you don't do properly, you need to separate them out, so the deformation it show a multiple step at a single step. People find out one is gradually. You want to etch it. This guy says that you need to etch it by multiple steps. Coming here, a pump die coming here, and then later coming here, something like that. All right, that's fair. Okay, single step etch. If you're doing a good job, stick together. Maybe some static develop. I don't know, right? But the multiple step, good. So how do you solve that problem? By the way, you have to make sure your nanosheet keep this rectangular shape perfectly. This is no good. It's no good. The reason that if it is rounded shape, then your gate control will have problem, your LG problem. So what do we do? Well, IBM and Lam had a JDP, Joint Development Program. And they can see that the vapor phase HCl, okay, but not that okay. Compare with the rectangular shape uniform CB channel by the dry edge. So they published paper in 2019, very good paper by Loubet, plus Loubet, a French guy in IBM, very smart guy there. Right? I think he worked with Lam to using a chemistry, which I discussed later. And this, I know, is ousted. This kind. Nobody want to do this. But what about applied material and tail? No words. I don't see any big announcement from them. So I don't think they did anything. Okay. Lam, once again, win the etch game. It's very strange. Intel not big about Lam, but TSMC is very big about Lam. I talked to one of the etch engineers, say, why is that? Why Lam, so popular in Asia? And the guy replied, stunned me. He said, Lam has multiple knobs in their machine, so it's easy to manipulate. And the other company has a fewer knobs, or they are not master in have multiple knobs in the machine. And TSMC work with Lam a lot. That's the biggest customer, right? TSMC. And they utilize the machine a lot. So TSMC's etch selectivity is like best in the world. Okay. And you look at the Lam report. They were the problem. So the machines called Argos, Prevost, and Celis, their selectivity is 1,000 to 1. And then the vapor SCO is like 20. And zero damage. Whatever you want to do, they have it. Precise surface treatment, precision here again. 1 angstrom. In real world step, see. Material loss control less than 1 atomic layer. So probably you don't need multi-step etch, right? It's good. They announced that fundamental change. I'm not sure about that, but the chemistry should be there. The reason I said so because this. If you look at the old book, late 2020, something like that, they have a paper published, it's a refer paper that infinity, this is the other way around. They keep the SiGe and etch the silicon. We're using CH4, CH2, F2, N2O2 mixture. They configure it, they tweak the machine, the knobs of the process, they come out with etch silicon like 800 nanometer per minute and 0 to SiGe. See that how vertical it is, how rectangular it is. So I think this is infinite selectivity, right? Compare with Lam's 1,000 to 1, I think equivalent. This is almost infinite. So this kind of chemistry can do that. I think you tweak it, you could do the other way around. So I think CH4 chemistry is what Lam used to develop this very nice work, right? Very nice high selectivity. Okay. But my comment to this is that it looks like foundry and tool supplier can solve the problem themselves. So what about IMT University? They don't have the machine for them. It's each machine at $3 million at least. They don't have the machine. So how can they contribute? They can only provide some ideas, but they're not useful in solving the real HBM problem. I'm sorry to say that. Because process technology advanced in such extent, only the big tool supplier and then the foundry can work together, solve a problem. University-wise, complete useless. I'm sorry to say that. But 2D effect. What's 2D effect? It's crazy. Molecular density and all that crazy stuff. You never enter into a real silicon roadmap, right? You look at that 1.4 nanometer silicon roadmap, it's still silicon. It's not, there's no 2D material coming in, right? I'm sorry. It is what it is. University need to do something else. Okay. So at the end of the talk, I want to take a look at the detail into TSMC 2 nanometer nanosheet. They announced it recently. 2020, next year will be HBM. Customer coming in, I think it's Apple, whoever, they completed 2 nanometer IP design in the silicon validation right now. The wafer test acceptance levels started. Right? So it will take a 1 quarter, something like that, maximum 2 quarters to validate. Once validated, they go out. And they say the internal SRAM is, wow, 90% yield. And I found no pattern about BDI. So, I mean, there's no relevant pattern for nanosheet about BDI. The meaning that they did not use SOI. Of course, they won't use it. It'd be crazy. It's a baseline change, not just the cost, Keep that in mind. It's a baseline change. If you switch to SOIs structure. I think they guess that my conclusion is that they figure out a good to stop, solve this butter issue. They solve it. POI is good enough. Maybe some slight tweak. Whether they introduce PIN idea, we talk about that. I don't know, but that's just one mask, right? And then look at sub-angstrom control everywhere. Look at their 3 nanometers selective selective etch for the contact, self-aligned contact. This is a self-aligned contact. The other aligned contact perfectly is optimized. Under, over, no good. And what I demand is that the hard mask corner here, 0.2 nanometer, 2 angstrom. In this corner cell, had to be less than 2 nanometer mass loss. That's just mass loss. What about the other material? So overall had to be sub-angstrom. That's why I meant sub-angstrom control everywhere. Okay. And this is what they say in 2022. Everything improved 15 to 25%. And they will introduce backside PDN. But did they do it? Did they have it? No, delayed. Okay. 2024, actuals. They introduced a flex, nano flex, the flex width modulation, all 3 nanosheet widths, 1 LG, all right? I don't think they manipulate LG, which I talked about later, all right? The one stack, 1 nanosheet stack is 1 LG. But they could change every different stack, they choose different LG for the short cell or tall cell, right? They could do that. So the performance, 15% delivered. But there's no backside PDN. I think its reason is this. TSMC moved from 3 to 2 is a big architectural change. They don't have a solid baseline, I'm sorry. Right? This is first generation for nanosheet. So they need to be very careful. Backside PDN is another big change. You need to thin down the wafer like, unbelievably thin. So that's not easy task. And so I think that's reasonable to say they don't have. It's okay. They didn't say there will be no backside PDN for the first generation. Maybe coming later. Hang on your head, right? What they say is that have a denser MIM capacitor, copper RDL. This is, I call, a evolution changes. Good enough. Another big thing they announced, I think is worth mentioning, is the scaling of the SRAM. This is a big deal. Because they didn't do that well from N5 to N3, and then to N3 to N2, they could reduce it pretty significantly. This is a big deal. Why I say it's a big deal? Because that means that their new baseline is healthy even with architectural change. This is hard. This is really, really hard. Because when you run experiment with a nanosheet, many new things pop up you never think is possible or occur before on a small volume. In a big volume wafer come out, you see tons of problems because it will be amplified a million times. And you don't see that, and you could shrink. That's amazing. And look at the Samsung. The first to introduce GAA 5 nanometer, and then 4, and then 3, and then 2, whatever. And then it's just struggling with the yield rate. And no mentioning of SRAM scaling much. Right? It's not easy. So it means that the baseline is really, really nasty good. And this is just FYI. I mentioned in the TSMC work before, right, in my last talk. They push back backside PDN, and then they improve they upgrade the aluminum RDL to copper, so to reduce the resistance by sizable reduction of via and a series resistance, and then they have direct the capacitors, deep trench capacitors. Deep trench capacitors, they do a 200 Intel 300. They have 200. Pretty good. Pretty good. They're better than before. So that's good enough for them. All these are CIP process, CPI, CPI, continuous process improvement. Should be continuous improvement process, CIP process. And generate its evolution. This is, I would say, revolution. But this is a revolution. You want to do two revolution in one time. Too risky. Don't do it. If you do go crazy, go like Samsung will break about it, the whole world fail miserably. TSMC is very conservative in that. And let's look at the nanosheet introduced something strange. Each nanosheet could have different length. You want an exact vertical, yes. But what happens if you have taper structure? And then the width is here, right? Is sum of all. What happened? Well, your W effective changes, so your sigma changes. Your sigma VT should change. That's a bad thing, right? That's bad. But AVT may be okay because sigma VT divided by W square root WL, which is the definition of AVT, because the W is actually wider than the previous generation. So maybe it's okay. So I'm guessing if this is the reason why TSMC can improve their baseline to the new architecture. I don't know. That's my wild guess. So before I leave the talk, are there other fancy knobs for backside PDM besides not four? I'm sorry. This one should be in addition to okay, backside PDM. Any other fancy knob? There is. This guy on Samsung. I know him well. That's his pattern. He said that this changed the channel width by playing with the spacer. The thin spacer, you have a wider channel, and then the thick spacer, you have a thinner channel. You know, he demoed with iMac. Very nice paper, very interesting paper. But and then the short channel can be, in fact, can be designed out. You can manipulate this and figure out if you have a very thin and wide sheet of silicon, should be fine. I agree with that. But how can you control this very nice? That's the question. That's the question. This compound hit his pattern, right? Now you change the spacer, spacer thickness, and you change the gate, so the channel. I think that's an interesting idea. That's what I meant that this is a fancy knob in addition to backside PDM. Why I said besides? You guys should say in addition to backside PDM. Sorry. So that's all, folks. Today we have discussed silicon, pretending silicon murmuring to germanium. Are you my Raman or my split? In many areas, they act like a Raman who will help silicon to achieve what silicon cannot do. But in many cases, they are just kind of a bad boy, destructive, especially with SiGeO2's existence. Clean is hard, DID is hard. And I compare Intel's IBM and TSMC in terms of 2 nanometer nanosheet formation. Currently, the winner, obviously, TSMC. And then the BDI, PTS, I think, bottom line, TSMC is still stuck with this, and stuck etch is pretty good. Everything is sub-angstrom control. That's why I make them successful. Okay, that's it, folks. Thank you very much.